Okay, the audience is coming in. Good morning and welcome to this webinar on the LCA of PEF bottles. The speakers today will be Ingrid Goumans, team leader of the technical application managers at Avantium, and Ángel Puente, LCA expert at nova-Institut. The webinar will be recorded and distributed to all registrants next week. And I will also put it online to the PEFerence project homepage for public viewing. Please put your questions in the Q&A box and not in the chat box. And Ángel and Ingrid will answer them in the last 15 minutes of the webinar. Yeah, we have now 185 registrants and a lot of them already dialed in. So I guess to keep with the time, let's start with Ingrid's presentation.
Great. Thank you. Thank you for the introduction, Freya. Yes, so thank you all for joining today. We will start with a short introduction also to Avantium and to PEF, and then Ángel will take over to present the LCA study that was conducted by Nova. So I think most of you are familiar with this. It is something that we see more often, but we see still a growing demand for materials, and at the moment we still see that a lot of these materials are coming from fossil-based feedstock, and for the growing demand we need additional material, and we need sustainable additional material. And if we then look at materials, then there are only 3 carbon sources that we can use to make this transition towards a sustainable economy, and that is either plant-based, air-based, or man-made. So the recycling, a lot of effort is put into recycling. But of course, also if we look at the growing demand and the losses that you still have during recycling, then we see that we have a major gap, and that gap needs to be filled, and that needs to be done via the other 2 routes. And if you look at air-based, so the CO2 conversion, that is still a relatively new technology. And for plant-based, there are multiple technologies, and one of them is also the product that we will discuss today, and that's based upon plant-based. So can you go to the next? Yeah, so who are we then as Avantium? So Avantium is really a company that is working on these 3 renewable carbon sources. So really to make that transition towards a sustainable industry, a renewable, and really looking at the renewable chemistry. So we are working on multiple technologies that enable this transition. So we are also working on CO2 conversion into chemicals. But as said, this is more early stage, and of course also our PEF products starting from plant-based, but we are also working on a technology to make bio-based MEG. So we see ourselves really as a pioneer in the renewable chemistry, so really helping in the transition towards a fossil-free future. So we are really, as said, a technology company, and we only work on technologies that help in the transition towards a fossil-free world. So this is our mission. We believe in a fossil-free world. Let's go. Then we go into a bit more detail of the process that we will discuss today. So our technology to produce FDCA and PEF. So here you see that the feedstock where we start from. So in principle, you can start from 1st or 2nd generation feedstock, but at the moment, only 1st generation feedstock is commercially available. So that's also where we will start with. And then we use the sugars, and those sugars can be converted into FDCA. So that's the technology we will discuss today, the conversion of the sugars towards FDCA, which is the main building block of PEF. And then the other 30% is plant MEG. You also see the Avantium logos. That has to do with the fact that we are also working on all these technologies, but they are on different levels of commercialization. So the LCA of today will really focus on our technology from sugar to FDCA, and then the polymerization of FDCA together with plant MEG towards the polymer PEF. And then PEF can be used in multiple applications like packaging, textiles, film. But PEF is also polyester, so it's also very well suitable for recycling. You can also enable closed loop. So these are also technologies that we are working on, because of course, if you bring a new material to the market, you also want to ensure that you bring it to the market in a circular, sustainable manner. So that is also something that we highly focus on. Yeah, so if you can go to the next slide. So I think we often compare PEF with PET, and that has to do with the fact that the two materials look a lot like each other. So we just looked at let's say the PEF value chain. If we compare PEF and PET, then you see that for PET, you start from crude oil. And there you also need two building blocks, being the MEG and the PTA. The PTA always comes from fossil based, but the MEG can, just as the MEG that we use for PEF, can come from plant. So you can have a 100% fossil-based PET bottle, or you can have a bio-PET bottle, and there only the MEG consists of plant-based. So only 30% of that bottle is truly bio-based. And for PEF, we replace the PTA part with FDCA. So it's a minor change, but it results in a different polymer. And it creates a 100% plant-based bottle and or material. So next to the fact that PEF is 100% plant-based, PEF has also superior properties. So if we compare it with PET, we see that PEF has better barrier properties. So what does that mean? That means, for example, we have a 10 times better oxygen barrier. So for sensitive products like juices, you can increase the shelf life, but also the CO2 barrier is better. So we can keep the carbon in and the oxygen out. Also, the water barrier is slightly better. We can process PEF in the same equipment as that you typically use for PET. And also what we see is that if we compare PEF and PET, that the modulus of PEF is 60% higher than that of PET. And that also enables lightweighting in combination, especially with, of course, the barrier properties. You have a great potential to reduce the amount of material that you need for your packaging. PEF is also not only used in bottles or in flexible films packaging, but we can also make fibers out of it. And I think there you also see a big challenge to have a very consistent material to make these very thin fibers. And there we also see that PEF is a very good material to make high quality yarns. And then if you look at the thermal properties of the two materials, it looks a lot like each other, but the glass transition temperature of PEF is about 10 degrees higher, and we have a slightly lower melting temperature. So that means that we process in the same lines, but we do need to adjust the process settings as such that you get best out of the material. So where are we with respect to scaling up this technology? So this is our roadmap. So we already have a pilot plant running in the south of the Netherlands for many years, where we have scaled up our technology from lab to a pilot scale. We produce 10 tons of material per year there, and it's quite an expensive process because it's such a small scale. And in that pilot plant, we collaborate with what we call our offtake partners, so partners that want to bring this material to the market in their application. And these partners will commercialize their products in what we call the flagship plant. So the flagship plant is a 5 KTA plant and is currently being constructed in the north of the Netherlands. And as said, we will produce 5 kilotons per year there. That flagship plant, currently under construction, will start up next year. And then, as said in the beginning, Avantium is a technology company. So the business case of Avantium is not to own and operate all these plants, but also to license out the technology that we have developed to also help in the quick scaling of the material to bring it to an affordable level. So the first license agreement has been signed. This is also announced. This is with Origin Materials. So that also means that the next phase, a 100 KTA plant, is in sight, where you also see that the price of the material will go down. So for the flagship plant, the price is still relatively high, which again has to do with the size. But then for the industrial 100 KTA plant, you already see that the price is coming down. So at the moment we have material coming from the pilot plant. It will be scaled up to the flagship plant that will go online as of next year, and the first license is already sold to Origin Materials. So I think that's going very well. And also the LCA will really focus on that technology that we will bring to market, and that will also result in these licensing plans. So on the next slide, we still have a picture of the construction in Delfzijl, which is ongoing. This is already a relatively old picture, so it's from November, end of last year in 2022. So at the moment, there is already much more if you go to Delfzijl. But it just shows that we are constructing the flagship and that it will be operational next year. So the construction of this flagship plant, but also many of the collaborations, and also the collaboration with Nova, it is all done partly under the PEFerence project. So we have a 5-year European flagship project to also establish this supply chain for FDCA and PEF. So we work with many partners in this project, and the objective of this project is also to engineer and build the flagship plant that you just saw, but also to demonstrate and validate the applications of the material, because of course you can build a flagship plant, but if nobody wants to put it into the market and commercialize it, it has no use. So that is also one of the key objectives, to demonstrate the applications of the PEF end products. And of course we also look at the social and environmental performance of these developed products, because we are doing this because we want to make the transition towards a sustainable future, and then that is also key, and that is of course also the key topic of today. So then we have one last slide that shows the project partners that are all in the PEFerence project. So for the feedstock, we have Tereos. Tereos will also be the feedstock supplier of the flagship plant. Then of course we we go from the sugar towards the FDCA. This is the technology that we as Avantium have developed, and Worley is our engineering partner that is helping also with the construction of the flagship plant. Then we have the polymerization of FDCA towards PEF, which is the technology of Avantium. And then we have many converters, but also brand owners. So OMV as a converter, but as brand owners, we have Lego, Henkel, Nestle, Carlsberg Group, LVMH, and there you also see that for example, with LVMH and Carlsberg Group and Henkel, we have also signed really offtake agreements, so that they will really bring it to the market as of next year. And then, of course, we work with Nova on the sustainability part, and Spinverse is responsible for the project management. So that's a bit of an overview on who's all working on this project. And then now we go to the most interesting part, and that is the LCA that was conducted on our technology. So I hand it over now to Ángel.
Thank you very much, Ingrid, and so welcome everyone. Good morning. So I will take it over from here. So the main focus of today's webinar is the LCA of Avantium's PEF, as Ingrid mentioned, as part of the activities that we are conducting in the framework of the PEFerence project. Let me first of all introduce nova-Institut. So nova-Institut is a partner in the PEFerence project. We are responsible for sustainability assessments in the project, but also for the dissemination and communication in the project. So we are a science-based consultancy with a focus on renewable carbon. So what we are doing is we are helping companies for the transition from a fossil-based economy to a renewable carbon-based economy. So we define renewable carbon as 3 different sources of carbon. One is bio-based, for example, the case that we are talking about today. The other one is CO2 based, and the other one is carbon coming from recycling. And we offer different services, like, for example, sustainability assessments. And I guess many of you attending the webinar, you are very familiar with LCA. It's a hot topic nowadays. But I can briefly mention what LCA is. So LCA is a systematic analysis of the potential environmental impacts that products or processes over their life cycle can have. And so the main framework is laid out in an international standard, the ISO 14040/44, and this is very important because so this ensures a minimum of transparency when conducting LCAs under this standard. It's also the most comprehensive evaluation for LCA that exists currently. And also one benefit of LCA is that it assesses and balances multiple impacts from greenhouse gas emissions, so the so-called carbon footprint, depletion from resources, but also impacts on humans and on the environment. And it can serve for many different applications. For example, it can support marketing, it can support also policymakers. But I think very importantly, it can support product development and improvement. So it can serve as an integral tool to assess process alternatives, even at early innovation stage. And so this is actually what we have done in the case of Avantium's PEF. Because we started supporting Avantium so with the first PEF pilot plan, so already 6-7 years ago. So it's not that we are presenting here the results of a single point LCA, but we have really been conducting this LCA for several years, and we have been supporting in the developing of the flagship plant. And this is particularly relevant to have this we call it the suited approach, the sustainability integrated technology development, because making use of LCA and of course other methods like techno-economic evaluation for early stage development can help identify and improve processes in a sustainable manner from the very beginning. So, okay, what is the goal of the LCA for Avantium's PEF? So we defined or we identified two goals. The first one is quantitatively assess the potential environmental performance of selected PEF-based packaging solutions, aiming at supporting the technical and capital decisions during the process development of the technology and also of the flagship plant. And yeah, in particular, we have focused so far on FDCA as a building block. We also have focused on PEF resin, but we also have considered different applications like PF monolayer bottles, but also PET PEF multi-layer bottles. I think it's important to emphasize that in this webinar we will focus on bottle applications, and this is very relevant because of two reasons. One is that if we only focus on the polymer, it disregards the in-use benefits of PEF. As Ingrid mentioned, PEF has so extraordinary barrier properties, and this is making this polymer especially interesting for packaging applications because it can allow lightweighting designs, and that's why we are here also targeting or focusing on bottles. And also packaging, I think, is also in general in LCA is a very interesting product because of the ubiquity and visibility of packaging, and also the growing concern for the environment, which is leading to many scrutiny of environmental impacts in the packaging sector by a variety of stakeholders. Of course, another goal is to compare these PEF applications against fossil counterparts. So in this case, we will refer to PET bottles. And the LCA was conducted following the ISO standards 14040 and 14044. But also, we also included some recommendations from the European standard, the European norm 16760, which has some additional provisions for bio-based products, which are missing in the ISO standard. And the results that we are going to present are also based on the critically review LCA, which was conducted by 3 independent reviewers. Coordinating, the chair of the review was the TÜV in Germany, IFO-Institut in Germany, and Ecomatters were also part of the review. So of course, a critical review is a process to verify that the LCA study has met the requirements for methodology, for data, for interpretation, also for reporting. And in particular, it's relevant to ensure that it's consistent with the standards. And also the review facilitates understanding and also enhances the credibility of every LCA. And so what I'm going to show today, so it's based on the critical review that was already conducted or already certified by ISO 14040 already 2 years ago. So here is an illustration of the life cycle of PEF with the PEF bottle application. So the LCA covers all relevant life cycle stages from cradle to grave. That is from the supply of materials to the production of the bottles, and including also their end of life. And here we are talking about incineration and recycling. So it is very important when considering the life cycle analysis, not to only evaluate, especially for packaging, not only to stop at the gate, but also consider the end of life, especially when we are comparing with alternative packaging systems, or even with materials with potential different end of life options. Because evaluating the whole life cycle allows a decision maker to also identify major contributors to the impacts, and this can be used for to develop strategies to reduce the impacts of the products. In terms of the scope of the study, so here the idea is to put a bit into context for a proper interpretation later on the results of the LCA. So for the geographical and technological context, so the feedstock of Avantium's PEF is fructose. So this fructose is produced in northwestern Europe via starch wet milling process. The scale of the technology, the exit technology from Avantium, refers to a scale-up 100 kiloton FDCA plant base, and it's in Delft in the Netherlands. Sorry if I'm not pronouncing for the Dutch people this place accordingly. And PEF polymerization was modeling, assuming toll manufacturing in Europe, and not assuming any specific location. The idea is that the LCA is representing a time frame for the first years of commercialization of PEF, when PEF is in the market from the flagship plant. I think we also have to comment on the energy that was used for the LCA, for the technology, for the exit technology. So for the heat supply, we consider steam coming from natural gas, and for the electricity supply, we consider the current mix in the Netherlands. As reference products, as we commented, so we evaluated the PET resin and also PET bottles. And we conducted assessment for a cradle to gate analysis approach, but also for a cradle to grave. So both results are available after the analysis. The end of life scenario, I will comment later or more details about it. But for the baseline, we consider the Netherlands with a 65% recycling rate for PET or PEF bottles. And regarding allocation of co-products in the value chain, so for the baseline we consider mass allocation, but of course we included different sensitivity analysis using other methods. So I've included also here a more detailed depiction of the system boundaries of both systems, so the PEF bottles and the PET bottles. We don't have to go, of course, now through all the details, but here the idea is to show that, of course, we in the main study we provided some level of granularity and that allows also to identify so which stages or which processes are better or worse or performing equally compared to the PET reference system. So a very important aspect of every LCA is data quality, because basically it's what then is driving the final results. And so we aimed at a very good representativeness of data, and I think we achieved that, because for the core process being the feedstock that Avantium is using, the core process, but also some end-of-life scenarios. So we use primary sources, primary data. In this case, coming either from Avantium, the data directly, or from the producer of the fructose in France. Also, PEF relies on bio-MEG for a 100% PEF. And so we model ourselves using EcoInvent this process for bio-MEG, but we also use data for the ethylene glycol production directly from Indian glycols, who is producing MEG from sugarcane, and is currently one or maybe even the only known global producer of sugarcane ethanol-based MEG. In general, so most secondary data is based on EcoInvent database. So this is a database that is internationally recognized from a qualitative perspective, but also from a quantitative perspective in terms of data that they cover. And yeah, overall, so the reviewers also validated a good data quality. And yeah, just to mention that we conducted a data quality analysis following the method described by Waidema, which look at reliability, completeness, temporal, geographical, and technological correlation of the data. For the end-of-life modeling, so for the end-of-life scenario, we based this scenario on a report, the UNUMIA report, published in 2020. So it's a report that presents a summary of the best available data for European PET, covering production, products on the market, collection and sorting, and also end markets of recycled PET. And in particular, in that report, so country-specific recycling rates for PET bottles are included. And for the baseline that I'm going to show today, I will show the case of the Netherlands, which consists of a 65% recycling rate for PET bottles and 35% of incineration rate. So in this study, also in this LCA, we assume, so because of course PEF is still not in the market, but we assume that PEF bottles will be recycled in the PET recycling stream until the market has grown sufficiently to enable an individual material recycling stream, which will produce recycled PEF. And so this assumption or situation is supported by Avantium, that they have an interim approval from the European Plastic Bottle Platform for PEF to enter the PET recycling system. And For the allocation at the end of life, yeah, we included two different allocation methods. One is the avoided burden, which, to simplify a bit, what does it mean, is including credits for material and energy recovery. And in other words, it focuses on recyclability of the material. But we also evaluated the cutoff approach, which means that recycling credits or any type of credits are not considered, but the focus is rather on the recycled content of the bottles. So one very important aspect of LCA is the functional limit definition, and this is very relevant if we are making a comparison. And so in this LCA, we focus on 500 milliliter, or I'm going to show the results of 500 milliliter monolayer bottles. And the function of the bottles were defined as serving for storing and delivering carbonated soft drink beverage by means of single-use recyclable bottles. Yeah, however, as a matter of design, so there are PET bottles in the market of different weights for a given volume. So in this sense, in order to ensure comparability, we imposed two properties that have to be met. One is the mechanical integrity, meaning so that the bottles they don't have to break or damage during handling and transport. And very important for this for PEF is the barrier property, ensuring a shelf life of minimum of 12 weeks CO2. That resulted in weights for PEF in the range from 16 to 19 grams for the 500 milliliter bottle, and for PET between 20 and 24. So in general, this improved barrier and mechanical properties of PEF allow for a reduction in material usage with respect to PET. And this is one of the main advantages of PET, which is also translated or seen in the LCA. In terms of environmental impacts, so we cover the impacts from the environmental footprint 3.0 method. This is the method recommended by the European Commission, and it covers 16 impact categories, the ones depicted here. And for the climate change, we included and excluded biogenic carbon update. So we showed the results with these two situations. And now we can directly jump into the results of the assessment. And here I'm selecting two of the most relevant impact categories, at least in the current political and societal agenda, which are the climate change potential and the use of fossil resources. And we can see that for the climate change potential on the cradle to grave and including the biogenic carbon sequestration, we see a 61% greenhouse gas emissions could be saved over the life cycle of a PEF bottle compared to a PET bottle, which is a significant saving, given also the maturity of PEF and the high established market and volumes of PET bottles. Similarly, we also see a significant reduction on the use of fossil resources of around 34%, here expressed as megajoules per bottle. If we look closer at the impacts, here I'm depicting, I'm showing the contributors of the climate change. And we can focus from zero to the right to see the environmental burdens. I will then later on explain the left part. But we can see that the impacts are evenly distributed among fructose supply, having a significant contribution, the ICSI technology itself, and then the bottle manufacturing. So to say, these are the main hotspots of the process. Of course, also bio-MEG, polymerization, and also incineration, they have a significant contribution, but the main contributors are bottle manufacturing, ESA technology, and fructose supply. On the other hand, we see the benefit of PEF being about 100% bio-based material, which can absorb CO2 during the feedstock growth. And this is also seen as a benefit in the LCA. And here then you see the credits in this avoided burden approach during the end of life for energy recovery, for the fraction of the bottles that are incinerated, and for material recovery for the fraction of bottles that are recycled and therefore having a subsequent use. If we can also do the same analysis for all the impact categories. I don't want to go through all the details here, but yeah, we can see that in some impact categories like climate change, use of fossil resources, particulate matter, the ESA technology can have yeah, some significant influence, but mostly for many impact categories, the main dominator, the main contributor is the fructose, so the feedstock supply, which is this green bar. And this is especially very relevant for many impact categories that are linked to agricultural activities, which are eutrophication, land use, acidification, etc. We can also do the analysis after normalizing and weighting the results using the normalization and weighting factors, also recommended by the method that we use, the European footprint method. And so this analysis revealed that the impact categories actually mostly contributing to the overall environmental footprint of PEF are the climate change, the use of fossil resources, and the use of minerals and metals. Being the other impact categories, most of them having a much lower relevance. And yeah, in particular, so these impact categories are mostly linked to these agricultural activities. And yeah, they were found to be significantly less relevant and contribute to a minor extent to the overall environmental impact of PEF bottles, even though, of course, if we look at absolute values or relative values, for example, if we consider the land use, we see that this is much higher than for PEF bottles and PET bottles, basically because yeah, we are evaluating value chains of a completely different nature. So one being bio-based and the other one being fossil-based. So of course, yeah, an LCA is not only a number. So an LCA study is a long document. In our case, I think it was 150 pages, more or less. So including many different sensitivity analysis. For example, different ways of valorization of co-products, different ways of allocating co-products, also different end-of-life scenarios, end-of-life treatments, recycling rates, but also very relevant, we also studied different bottle weights, bottle volumes, different bottle systems like monolayer, multi-layer, and also we are currently assessing in the framework of the project other products beyond packaging bottles. So one of those sensitivity analyses that we conducted is recycling rates. And so how the results of PEF and PET vary with the recycling rate, because yeah, we know that the end of life and the final fate for the bottles can have a significant influence on the carbon footprint results. And therefore, we evaluated the sensitivity of the results with the full range from 0% recycling rate, meaning 100% incineration, to 100% recycling. And we can see in the baseline scenario that we used this current recycling rate of 65% in the Netherlands. We observe a 61% greenhouse gas savings for PEF compared to PET. If we look, for example, at a country with a deposit system highly implemented like Germany, we can see higher carbon footprint savings. And here you see also if the full PET and PEF bottles will end up in being recycling. So 93% savings of PEF compared to PET was observed. And even in the worst case scenario, because for this sector, for packaging, the trend is towards recycling, but even in a worst case scenario, 44% less greenhouse gas emissions will be emitted for the PEF bottle compared to the PET bottle. Another interesting analysis that we conducted is what is the impact of PEF and PET for different bottles already containing some recycled content. And we can see here from 0 recycled content, so a 100% virgin bottle, to a 100%, so a fully recycled bottle. We can see the evolution of the carbon footprint of PET and PEF. And very importantly, also, if we consider just the PEF bottle, the virgin, with no recycled content, we can see that the break-even point is at a level of 63% recycled content of PET that will equal the carbon footprint of a virgin PEF bottle. I think it's important to mention that nowadays the average recycled content of PET bottles is around 11% in Europe, and also that by 2030 the packaging and packaging waste regulation is establishing or is setting up a target of 30% recycled content for PET bottles for food contact, and with these levels of recycled content similar for PET or for PEF, we will end up in 46% greenhouse gas savings compared to PET. So I will skip. I will go now to the resin, because we have now just commented bottles. But of course, you might wonder also, okay, what happens with PEF alone with the resin in this case? So this is a cradle-to-gate analysis, not anymore a cradle-to-grave. And we also conducted some prospective scenarios, and we see that even so in the baseline already we observe a 60% greenhouse gas savings compared to PET. But then if we include additional improvements, for example, including the Ray MEG technology that Avantium is developing into the PEF production, or even switch to a complete renewable electricity in the ICSI process, or the heat coming from biogas, so we can see the influence of these improvements, which are best case if these measures are integrated in the development of the plants. We can even say a best case reaching almost the carbon neutrality. And that when we compare to PET produced in Europe, of course, even better comparisons are obtained if we compare to PET produced in other countries, as for example China, with a lot of imports here in Europe from China. So this is in general a very good results, especially if we compare that PEF is a young process technology, and we are comparing with PET, which is a highly commoditized material. Also, this is not part of the analysis that has been critically reviewed, but we are currently also conducting analysis on second generation PEF production. And yeah, we can see that something around 30% of additional greenhouse gas reductions could be expected by this switch to second generation feedstock. But as I said, this still has not been critically reviewed. And very briefly, so if you are interested to read more about PEF, so very recently this year, we also published a scientific publication in a collaboration with the University of Utrecht, the Copernicus Institute, which is focusing on PET and PEF bottles using the data of this LCA that I've shown today, but with more details about the end of life. So here they studied mechanical recycling, chemical recycling, and further details on. I will not comment much more about this paper. You can have a look at it, but more or less they found similar and greenhouse gas savings as we found in the PEFerence project in the study. So I think some takeaways is of the LCA of PEF is that despite of the small scale and young process technology, the PEF resin can compete with highly commoditized PET, and there is still some improvement potential because PEF is in development. Basically, these benefits in the LCA are mostly coming from the improved performance or properties of PEF, being the barrier and the mechanical properties, which enable for packaging lighter designs and therefore material savings. And we observe significant CO2 savings and also less finite resource consumption of fossil fuels compared to PET bottles. And so these impact potentials are two of the most relevant impact categories in the current political and societal agenda, driving the transition from fossil to renewable carbon. So therefore, we consider this was a very good result. And we also identify that the impacts linked to agricultural activities were found to be significantly less relevant and contribute to a minor extent to the total environmental impact of PEF bottles. And PEF relies 100% of renewable carbon and contributes to stop the release of additional CO2 to the atmosphere. So will play a role in the absolute reduction of global greenhouse gas reduction. And that preliminary assessments also indicate that 30% additional greenhouse gas emissions reductions could be achieved by switching to second generation feedstocks. And with this we come to the end of the presentation. So thank you very much. If you have some questions, you can contact us by email. And now, so we are happy to answer some of your questions.
Yes, thank you for asking your questions. We have quite a lot. I think I will start with the ones regarding the LCA. The first one is, as for end of life, only incineration was considered, right? Meaning all biogenic uptake was released back again.
Yes, so this was considered. So I showed this graph. And you see, so this result will be this consideration.
Then someone congratulates you to the LCS study and the PEFerence project and asks, since EF methodology does not allow the uptake CO2, how did you deal with this limitation for the study?
Yeah, so first of all, we have to consider that, or we have to understand that the environmental footprint method does not, let's say, it recommends not to use the biogenic carbon uptake, but it's not saying that it's not allowed. So it always allows for an additional calculation. So therefore, we decided to report both values. So one without the biogenic carbon and the other one with biogenic carbon uptake. Very recently, so this year, also now there is a new available environmental footprint method in which now this possibility is also there to include the biogenic carbon uptake.
Emissions reduction for the plus renew electricity scenario seemed pretty low. How can this be explained?
This is wait a second, I try to find the slide. Yeah, it's not so, it's significant still. So if we compare the baseline to the renewable electricity scenario, is still 18% less greenhouse gases. So we are only considering here renewable electricity for the ICSI process. So we have not, throughout the whole model, we haven't changed the electricity consumption, for example, for bottle manufacturing, which was also one of the hotspots of the process and actually consuming quite some electricity. So this is only for the fraction referring to the ICSI process. And in the ICSI process, I think the energy in form of electricity is not the main hotspot. Keep in mind also that during some dehydration and oxidation process in the ICSI process, also some energy is generated that is internally reused. So electricity is not one of the hotspots of the ICSI process.
Okay. And one question, the first one actually is PEF recyclable in current streams? You touched that topic, but maybe.
Yes, I can take that one. Yes, PEF can be recycled in the existing streams. So as Ángel also briefly mentioned, we have an approval of EPBP. We had our interim approvals, given PEF is not yet commercially available on the market, but we have an interim approval of 2% mono PEF bottles in the PET recycling stream, and we have also one on multi-layer bottles, where 10% of that bottle consists of PEF, and that is in Europe. And also quite recently we received the APR approval, that is in the US, also for multi-layer PEF PET bottles with 10% PEF layer, where PEF is used as a barrier. And yeah, what we see is PEF is just like PET, it's a polyester, and one of the reasons why PET is so well recycled is because you can recycle it also back to a food contact grade. It's a polyester, it has living end groups, so you can build up molecular weight again that you lose during processing, so you can really bring it back to a material that behaves in the same way as the virgin material. PEF is also polyester, so you can do exactly the same. It also works the same as how you would do it for PET. If you recycle it together, as you remember maybe from the beginning, we only changed the PTA to FDCA, so the MEG part is known for PET. The FDCA is something new, but it are two polyesters, so they will react with each other, they will transesterify, and you will build in the FDCA in PET, creating a copolyester. And this is something which for PET, in principle, it's never 100% PET. They also always make use of some monomers to get the required properties in the material. So in principle, FDCA is doing the same.
Thank you.
Yeah, and maybe a good thing there to add also is that also PEF has its own fingerprint. So at a certain point, if you have enough volume of a material, you can even sort out the PEF via the typical sorting system, so the near infrared. So you can sort out PEF and create an own stream once the volume is big enough to set that up.
Mm-hmm. Then another question on the LCA. Did you consider the end of life in the environment and the impact on PEF versus PET? The impact of PEF, I think.
Sorry, I didn't get the question right.
Did you consider the end of life in the environment and the impact of PEF versus PET?
Yes, so so it's what I showed for the bottle application is a cradle to grave, and the end of life was considered in the evaluation. So in the baseline we consider 65% recycling for PET and for PEF, and 35% incineration for PEF and for PET. And if the question is whether for PEF in the incineration the burden is included of incineration, yes, because we for the carbon modeling we use this -1+1 approach, meaning we consider an uptake during feedstock growth, but we also consider a release of CO2 upon incineration of PEF is also contributing to the carbon footprint.
Which end-of-life allocation method was applied? Cut-off? What happens with the uptake if recycled? When will it be released again?
Yeah, very good question. So we used, it depends on the type of question that you want to ask. For example, for such an analysis in which we focus on recyclability, so basically recycling rates, and you give, so to say, the benefit to the material for being recyclable. Here we use the avoided burden approach because it's the only method that is is answering this type of question in LCA. Whereas for this type of analysis where we focus on recycled content, we focus more on how much material is coming from secondary and from a preliminary use of a previous use of the materials. We used the cutoff approach. And in the cutoff approach, so to say, then the benefits at the end of life are not shown. To the question, what happens with biogenic carbon with recycling? This is a very difficult question. It still is under discussion. It's not solved in the ISO standards how to deal with that. For that, you know that there is something that is not avoided burden, not cut off, something in the middle, which is a so-called a circular formula or end-of-life circular formula that, for example, the environmental footprint, a product environmental footprint method recommends. And in that case, also the benefit of the benefits and the burdens can be distributed between the primary use and the secondary use of the bottles. But for the moment, in the cutoff approach or in the avoided burden, we assigned the benefit of being biogenic to the virgin production, because it's basically the ones having the influence about whether to produce a bottle bio-based or fossil-based. In other words, if some bio-based material is passed through recycling to another cycle, the secondary user of the bio-based material cannot assign additional burdens because being bio-based, because it's actually just a recycling stream. Bio-based has more influence for the first cycle, for the virgin production.
Mm-hmm. Is PEF considered generation 1 bio-based?
Yes, so the feedstock that we will use from the flagship plant that comes from Tereos and from wheat. And in principle, what Tereos does is they have many products coming from that wheat. So they take out the protein, which is the most valuable part, and that's also where we are in need of. And these proteins are used in, for example, plant-based meat, but also that part goes into making bread out of it. And then they have also the starches, and those starches are converted into many different products, alcohols, sugars, and one of them also being the high fructose syrup, and that is what we are using. So it are really the carbohydrates. And we are not in a lack of carbohydrates, but it comes from wheat, so it's considered to be generation 1. Yes.
Is PEF compostable? If so, how long it will take to decompose fully?
No, PEF is not compostable, but we have done a study under industrial composting conditions, and there we did see that within 1 year, PEF degrades up to 90%, but this asset is under special conditions, industrial composting conditions. So this is not something that will just use when you have PEF in your packaging, or that it will start to degrade. So PEF is not considered to be degradable. That's also not the end of life that we foresee for PEF. It's a product, a material which is very suitable for recycling. So we also aim to put it in the market as a circular product. It does not lose its properties during use, but the industrial composting conditions does show us that something happens. So we really see it as a safety valve. If it accidentally ends up in nature, something that of course we don't want, but it can happen, then it will not stay there for hundreds and hundreds of years, what we typically see with fossil-based materials. But how long that process is, that is something that we are still evaluating.
Yeah.
Because there are many factors playing a role there.
Okay, thank you, Ingrid. The time is over. We have still a lot of interesting questions open. I think we will try maybe to answer them and then put them online on our project website maybe. I will inform the registrants how we proceed with this, and the recording will be sent out to you next week. Thank you, Ángel and Ingrid. And thank you to the audience for joining us. Have a nice rest.
Thank you all.
Thank you.
Bye-bye.
Bye.